In this video, we're going to examine the scalar equation of a plane in space. So consider a plane with a given normal n. So this is our plane, and this is its normal. The normal vector will define the direction of the plane, but not the position. So for example, if you have a normal to this plane, that is also the normal to a parallel plane underneath it. Remember, we can anchor a plane in 3D space by having a point on that plane. So if we also have a point on the plane, we can then write the equation for that specific plane. If not, you can have infinite parallel planes. So you need a point on the plane to locate that plane in 3D space. We will do this using a similar method to writing the scalar equation of a line. So find the scalar equation of the plane, which is perpendicular to the normal, defined as 5, -1, 6, and contains the point 2, -3, and 4. So what we're going to do is we're going to start by setting another point on the plane. Okay, and so I'm going to go ahead and I'm going to define that as being some other point on the plane. So I'm just going to go put another point on the plane. Okay, we'll say like right here, for example. Okay, that's my other point on the plane. And what I can do is if I have another point on that plane, I can then create a vector on that plane that goes from point or P0 to P. And if that vector is on the plane there, that vector will be perpendicular to the normal because the normal is perpendicular to the plane, and therefore the normal is perpendicular to the vector on that plane. So this is what I'm going to do. I'm going to create a vector P0 P. So that's the first thing that I'm going to do here. So I'm going to say, second, create vector P0 P. Right, and that's that vector that's on the plane right there, P0 P. Just show you again. P0 P right there, okay? And it will be perpendicular, I can even draw that in, perpendicular to this normal. Okay, let's go back and create that vector. Okay, and we create that vector by going final minus initial. So my final is x. My initial is, my initial is 2, so x minus 2. Y minus -3, and then z minus 4. Okay, so that's my vector on the plane. What I know is that this vector, P0 P, dot product with the normal vector should be equal to 0. So I'm going to go ahead and fill that in. X minus 2, y plus 3, z minus 4. And I'm going to dot product that with the normal vector, which is given to me as 5, -1, and 6, or rather -6. And I know that that dot product must equal to 0 because they're perpendicular. Okay. Proceeding with the dot product algorithm, 5 x minus 2 plus -1 y plus 3 plus -6 z minus 4 is equal to 0. All right. I'm going to go ahead and expand this out. 5x minus 10 minus y minus 3 minus 6z plus 24 is equal to 0. And then what I'm going to do is I'm just going to clean this up a little bit. 5x minus y minus 6z plus 11. is equal to 0. And now, as you can see, I have an equation that defines the plane. And I use this equation as a scalar equation, and we call it a scalar equation because there are no vectors involved. We've gone from using vectors, the vector on the plane, dot product with the normal vector to the plane, and now we've created an equation without any vectors, and that is the scalar equation of the plane. So as you can see, ax plus by plus cz plus d is equal to 0, and that's my scalar equation of a plane. Okay, so let's keep going. We can see right here that this was done using a very specific normal and a very specific point. But let's now develop this using more general terms, right? So instead of having an actual point, we say x naught, y naught, z naught. Instead of having numbers for the normal, I'm going to use a, b, and c. Okay, so let P be any point on the plane. P naught P is in the plane, so therefore P naught P dot product n must be equal to 0. Okay, so the first thing that I'm going to do is I'm going to define P naught P. P naught P is the vector that's in that plane, right? And so I go x minus x naught, x minus x naught, y minus y naught, z minus z naught, and that's my vector P naught P. My normal vector has been given in the question, a, comma b, comma c. Okay, and remember that the dot product of these must be equal to 0, because if the vector is in the plane and the normal is perpendicular to the plane, then the normal is perpendicular to that vector. So that dot product must equal to 0. So again, I can say, all right, well, x minus x naught, y minus y naught, z minus z naught, dot product with the normal vector a, comma b, comma c must be equal to 0. So what I'm going to do is I'm going to expand that all out using my dot product algorithm. A, x minus x naught, plus b, y minus y naught, plus c, z minus z naught is equal to 0. Cleaning this up, ax plus by plus cz, and then I'm going to have minus ax naught from this expansion right here. So recall that I'm expanding all of these coefficients into the brackets right here, and here, and here, okay? And that's where I got my ax, that's where I got my by, and that's where I got my cz. But now I have to deal with the negative ax naught, negative by naught, and negative z, or negative c z naught. So negative by naught, negative c z naught, and that must equal to 0. Because x naught, y naught, and z naught is a specific point in the plane, all of this right here will be a constant, and that will be constant d. Okay? And so now we can say, more generally speaking, ax plus by plus cz plus d is equal to 0, right? And I know that my d was simply just this constant right here, which is negative ax naught minus by naught minus cz naught. So d is equal to negative ax naught plus by naught plus cz naught. Okay, continuing on. We can now write the general definition of the scalar equation of the plane, given as follows: ax plus by plus cz plus d is equal to 0. And you'll note that a, b, and c are components of the normal vector. And then a cross b was the normal vector. So your basis, the cross product of your basis vectors makes that normal vector, right? So we can see right here, a, b, and c were the components of the normal vector. Those are now the coefficients of x, y, and z in the scalar equation of the plane. This is very similar to the scalar equation of a line in 2D space. Okay, so it says find the scalar equation of OP, and right here I've got the vector equation of a plane. So recall that what I'm going to need here is I'm going to need a point on the plane. And I have that point already. That point is right here, 7, -2, 3. And the other thing that I'm going to need is I'm going to need a normal vector. Well, how am I going to get this normal vector? Well, recall what we have written right here. The normal vector is simply just the cross product of the basis vectors. So if I have two vectors, two non-parallel vectors on the plane, or non-collinear vectors on the plane, I can take the cross product of that, and the cross product, recall, is the vector that is perpendicular to those two vectors. And look at what I have right here. I have, in fact, the two basis vectors on my plane. So this is vector A, and this is vector B. So I can find vector n by simply taking the cross product of A and B. So let's go through that algorithm. A is 1, 2, -4, cross product with -3, 5, and 1. And so I'll do a little side work here, and I'll come up with the cross product. Okay. My cross product will be 22, 11, 11. And you might look at that and see like, well, I think I can reduce that, right? And absolutely you can, because the size of the normal vector doesn't matter. And what I mean by that is, take a look at this plane right here, right? I've got a normal vector here. The size of this vector doesn't matter, because if I had a normal vector that was half that size, right? Maybe you can't really see that. Let me do it a little in red, and I'll put it over here, okay? If I have a normal vector that is half that size, that doesn't change the fact that it is still normal to the plane. So the magnitude of the normal vector doesn't matter. So if I have a vector here that I've given my normal vector as 22, 11, 11, I can rewrite that as simply just 2, 1, 1. That vector is still perpendicular to the plane. Okay, so now what I have here is I have my A, my B, and my C. And you will recall from the definition of the scalar equation of the plane, ax plus by plus cz, a, b, and c are the components of the normal vector. So what I'll just write here is therefore 2x, that's my a value, plus 1y, well, that's my b value, so I'll just write y, plus c, and I don't know what d is yet. And even though I've previously defined d as being the negative of ax naught plus by naught plus cz naught, so a, b, and c times the x, y, and z components of the point on the plane, I can actually just sub in the point on the plane to find d. So I'm going to sub 7, -2, 3 to find my d value. So 2 times 7 plus -2 plus 3 plus d is equal to 0. And therefore, when I rearrange and solve, I'll find that d is equal to negative 15, and now I have my scalar equation of the plane. 2x plus y plus z minus 15 equals to 0. One thing that is of note is that generally we keep the x coefficient positive. All right. Now, so far we've managed to do that without having to modify it at all. But if your x coefficient happens to be negative, we're going to multiply the whole thing, every single term here, by -1 so that we ensure that our x coefficient is positive. Obviously not an issue here, it's already positive, but just in case you ended up with a negative coefficient in front of x, just multiply everything by -1 and you'll have a positive x coefficient. Okay, next question here. Find the scalar equation of the plane containing the points P, Q, and R. All right, so if I make a little plane here, okay, so I'm going to go ahead and I'm going to create a plane. Okay, so that's my plane right there, okay, and it's tilted to give you the illusion of being in 3D space. Okay, so I've got P, I've got Q, and I've got R. 3 points on the plane. So you might be wondering, well, how am I going to get a scalar equation of the plane containing these 3 points? Well, if I have these 3 points, what I can do is I can construct basis vectors on this plane by connecting P to Q and P to R. Alternatively, I could have done P to Q and Q to R. That would have been fine too. Those are still basis vectors. But I'm just going to do PQ, PR. I'm going to keep the tails together. Okay, so let's go ahead and create those basis vectors. So PQ is going to be equal to -6, -2, and 3, and PR is going to be equal to -1, 2, and -1. And you might be wondering, how am I getting those? Well, I'm just going -4 minus 2, -6, 1 minus 3, -2, 2 minus -1, 3, and the same procedure to find PR. Now that I have these two vectors, I can find a normal vector to this plane. And there we go, that's my normal vector. And you might be wondering, okay, well, how do I find that normal vector? Well, remember, if we want to find a vector that is perpendicular to two vectors, that is simply the cross product of those two vectors. So I'm going to find normal vector, which is simply equal to PQ cross PR. Okay. So again, I follow my cross product algorithm using these two vectors, and I'm not going to go through it. I'm just going to give you what the normal vector is. It's 4, 9, 14. Okay, now I have A, B, and C, so I can write this out. I apologize, 4x plus 9y plus 14z plus d is equal to 0. I'm going to sub in a point, 2, 3, -1 to find d. 4 times 2 plus 9 times 3 plus 14 times -1 plus d is equal to 0, and therefore d is equal to -21. And now I have the scalar equation of the plane, that being 4x plus 9y plus 14z minus 21 is equal to 0. And I got that from 3 points on the plane. Okay, find the vector equation of the plane for given this scalar. So we're going to go backwards now. So if I want to find the vector equation of the plane, remember the first thing that I need to do is I need to find basis vectors B. And the other thing I need is I need a point on the plane to anchor that plane in 3D space. Okay, so here are, this is what I'm going to do. So if this is my scalar equation of the plane, I can very easily generate points on the plane. And as you can see from the previous question, all I need is 3 points to define a plane. So much in the same way you need 2 points to define a line, you need 3 points to define a plane. Okay, so how can we easily generate 3 points? Well, quite easily actually. One way is we can set both y and z equal to 0. And if we set both y and z equal to 0, then I get x plus 4 times 0 minus 2 times 0 plus 8 is equal to 0. So we get x plus 8 is equal to 0, and x is equal to negative 8. So therefore, I have a point on the plane. Negative 8, 0, 0 is a point on the plane. Right? I'll call this one P. Okay. I'm going to do the exact same thing now to find a point for y and a point for z. So if I want to find y, I'm going to say set x equal to 0 and z equal to 0. So then 0 plus 4y minus 2 times 0 plus 8 is equal to 0. And then y is equal to negative 2. Okay, so therefore q is just 0, negative 2, 0. Okay, the last thing that I'm going to do is I'm going to see if you can figure this out yourself, but I'm going to set x is equal to 0, and I'm going to set y equal to 0. So 0 plus 4 times 0 minus 2z plus 8 is equal to 0. Z then would be equal to 4. Okay, so my point R on the plane is 0, 0, 4. Okay, and now that I have 3 points, I can now find basis vector A, because basis vector A will simply be P to Q, right? So if you want a better visualization of that, I can just quickly create a diagram for you. Okay, so again, I have a plane. I have P, I have Q, and I have R. Okay, so now I can very easily create basis vectors. Here we go, P to Q. And I can also create one, P to R. Okay, and those, in fact, will be my basis vectors. Oops, excuse me. A and basis vector B. So let's find basis vector A. Basis vector A is simply the vector from P to Q. And so all I need to do is I need to take Q minus P. Okay, and so that is going to be 8, negative 2, 0. My basis vector B is P to R. And P to R is simply going to be 8, 0, and 4. Okay, remember that the vector equation of a line is given as, and I'll write it generally, OP, which goes from the origin to any point on the plane, so it points from the origin to any point on the plane, is equal to the origin to a point on the plane plus a scalar value of A, and then plus a scalar multiple of B, where S and t are elements of all real numbers. Looks like I have A, looks like I have B, and looks like I also have a point on the plane right here, negative 8, 0, 0. So there we go. I've got my vector equation of the plane, which is negative 8, 0, 0 plus s 8, negative 2, 0 plus t 8, 0, 4, where s and t are elements of all real numbers, and there's my vector equation of the plane. Okay, we're going to create a little summary here of equations of planes, okay, and recall that we can have a vector equation of the plane where we have OP is equal to OP naught plus SA plus TB right here. We're looking at this one. Parametric equations, scalar equations or Cartesian equations, that's what we just studied right now. We do not have symmetric equations. Okay, here we go. To find the vector equation of a plane, what we need is we need 3 non-collinear points on the plane to find the vector equation. Or we can simply have a point and 2 basis vectors that are non-collinear. Okay, so they can't be parallel. They have to be at an angle to each other. If we want to find the scalar equation of a plane, we need a point and a normal. If we don't have a normal, we can just find 3 points, create a normal, right? And then we can find that out, okay? If 2 planes are parallel, just like we saw right at the beginning, let's scroll really quickly right up to the beginning. If 2 planes are parallel, they will have the same normal. So let's go back and fill that out. Okay, if 2 planes are parallel, they will have the same normal. If a line is in a plane, any point on the line is also in the plane, and the direction vector for the line is also a vector in the plane. All vectors parallel to a plane are also in the plane. Remember, if a vector is parallel to a plane, we can move a vector around in 3D space, provided that we maintain its magnitude and direction. And if a vector has a direction that is parallel to the plane, then we can shift it down without changing its magnitude and without changing its direction, and it will sit on the plane. If one plane is perpendicular to another, the normal vector for one is a basis vector for the other. Okay, so if you have 2 planes that are perpendicular to each other, the normal vector for one of those planes will sit on the other plane and therefore form a basis vector. If 2 planes are parallel, any vector in one plane is also a vector in the other. That's pretty similar to what we saw here. And a plane equation can look like a line equation if one of the components of the normal is 0. Right? So for example, in this case, maybe the normal vector, right, had a component of z that was 0, so 3, 4, 0. And as you can see, that's your A, that's your B, that's your C, and if 0 times the z variable is present, then we won't write the z variable, and then we just have this right here. So that looks like the equation of a line, but it's also the equation of a plane. Okay, your check your understanding work is given right here below. Thanks for watching.